Now we're on to traffic elements. So the category of traffic elements has several different subcategories. How to identify traffic signals, how to identify road signs, construction zones, pedestrians, weather, and emergency vehicles and conditions. So we'll do the same thing here for traffic elements. Traffic signals, look at this picture. As human beings, this looks like a simple problem. I can tell that it's a traffic signal and I can tell it's red and I know what to do. But then you start to read patents and you will be amazed at how hard it is to figure this out. Here we go. Here's the first group. I think there's a good number of maybe 12 or 14 different patents addressing identification of traffic signals. How to map and detect a traffic signal, access a set of images associated with the geographic location of the signal. From that image set, generate traffic signal labels. Is it red, yellow, or green? And then filter other red, yellow, and green objects from that image that aren't associated with that traffic signal. And then based on the filtered data and the traffic signal labels and the geographic location, determine the status of the traffic signal. Wow, we made something that seems really simple. All of a sudden, we realize how difficult it is. The next group of them relates to the status, how to classify a traffic signal status, how to determine the illuminated portion of a traffic signal, and how to estimate a state of the traffic signal. So we have different ways of doing that. We can calculate a score indicating a level of confidence of whether it's red, yellow, or green. We have an image portion that we have a score for the center of the portion and a score for the outer edge of the portion to see if they match up. And then the bottom one, we have a state of traffic signal based on sensor information and the state of the traffic intersection. So are the other cars moving or not? We can use that to help with our uncertainty regarding the state of the traffic signal. Here are some things, though, that a computer might be better at than human beings, and that is predicting the future state of a traffic signal. And so we have a number of patents related to that. How do I predict the future state based upon the time that it was, the timing from the previous day or the previous hour, and see if a drift has occurred between the beginning time versus the ending time at a given color over a 2 consecutive day period. That's a very specific patent. We can also do it by determining a first estimate based on a different traffic signal. So I know that these 2 traffic signals are timed together. I can estimate that way. I can request the state of a traffic signal other than the one that I'm approaching and use that to determine the state of an upcoming traffic signal. I can estimate the state of an upcoming signal based on the relationship between a different signal. These are all kind of similar. They're probably part of the same patent family. So the deep dive reading of the claim language would be where you might differentiate, but the approaches are pretty similar. The bottom one, how to determine the presence of traffic controls, receive movement data indicative of an intersection. Detect a pattern of velocities within a distance near that traffic control signal to find out if you are at a red light or a green light. So there we're predicting. Now we get to the even more difficult problem of inferring the state of the traffic signal. If, for example, we can't actually see it, there might be a truck in our way, or there might be a tree blocking it, who knows what. How do we infer the state of a traffic signal based on surrogate data, obtain sensor data from the vehicle environment, and use an inference system based on the environment not observed by the sensors to determine a confidence level? Another way we can do that is use another vehicle's brake light status. Another way we can do that is look at other vehicles' status of movement or non-movement. And the last one is receive an auditory information signal from a crosswalk to determine the state of the traffic signal. So a number of ways of not even having to see the traffic signal and infer the state. There are 2 more still. How do I prepare for a traffic signal? I can determine the location of the traffic signal and the distance from it. And if it's greater than a threshold, I can decelerate to obtain additional information about the signal. And the final one, how do I respond when the traffic light is about to turn from yellow to red? That is a very interesting problem to solve. Determine the location of the vehicle as being in or not in the intersection and proceed through the intersection if it's determined that you are in the intersection and it just turned yellow. That's how we all act when we see a yellow light, just like that. Okay, that is the traffic signals section. Here are some pictures. Here's one, if you can see on your screen, there's a little gradient above the illuminated area. There was one with the truck, I thought. Let's see, where did that one go? Here's one where the truck is blocking our view, so we need to infer the state of the traffic signal. Here's one where some people are turning and some people are stopped. We can infer, and so on and so forth. All right, next. Road signs. How do we read road signs? Good question. Let's find out. First, I need to detect the road sign, and then I have to determine the context of the road sign. I receive images, and I detect candidate objects from those images, and I perform some sort of a cross correlation between a template of the image and detect the colors, and from that I can determine the shape. And from that, I can determine what kind of a sign it is and what that means to me as a driver. Going to the context side, how do I decide whether I should respond to a stop sign? So, interesting problem from the autonomous point of view. I can identify a stop sign, but I have to also know if it's a stop sign that actually applies to me in my lane. I have to determine whether the stop sign is it temporary or not, and compare it to map data and determine whether to respond to the stop sign based on the direction the stop sign is facing, and also using a threshold height and determine if it applies to me. All right, there's a good one here is a picture of a school bus. So there's a stop sign that is not going to be in your map data, but something that you're going to have to determine whether or not you need to respond to. That's what that particular 10 million patent applies to. Okay, construction zones. Here's another one where your map data is not going to be very helpful because the lane that you expect to be there is not there. So we can imagine this being a difficult problem to solve as well. First of all, I need to be able to detect a construction zone. How do I detect an object in the construction zone? I use a 3D point cloud, an area representing the road surface. I identify construction zone objects and the number of them and the location of them, and I determine from that the likelihood of the existence of a construction zone. How do I detect a construction zone sign? Use a LiDAR-based information to detect information in the vicinity of the road at an expected height and with an expected shape to tell me that it's a construction zone. So I can detect a construction zone just by a sign, or I can detect it by a sign plus other objects, different ways to detect that. How do I classify a construction zone as active or inactive? I map an area of a construction zone based on an object and its classification, and I add it to my detailed map. And I identify a second construction zone object and update the area and the construction zone and classification based on that information. Next, with construction zones, just identifying them isn't enough. We also want to know the severity of the construction zone. And so we have a few ways of detecting that. I can identify the shape and the heights of the construction zone sign and the objects, and from that I can calculate a severity, or I can detect construction zone signs and cones and barrels, and based on the number of them and the location of them, that will be used to determine the severity. Or I can detect that a traffic sign is missing, and that can be a signal that something has changed and a signal also of the severity of the change. And last is the response to the construction zone, how to detect and respond to the redirection. Drive using your pre-stored map information, including traffic flow directions, but then receive a perception of system objects relating to traffic redirection, not located on my map, and used my sensed data now to identify the corridors of traffic redirection and select the corridor based on the direction of traffic flow. So I'm actually going to see where are other cars going to determine what traffic flow I should start to follow. All right, here's all the, for whatever reason, there's a lot of prettier pictures in the construction zone patents. There's counting the number of pylons, there's seeing the sign at the right height, there's real construction vehicles and everything else going on. And here's someone finding a new path to take because of the construction severity and so on. Okay. And construction's not enough. There's other problems that arise when we're driving. We run into pedestrians. We don't run into, we try not to run into pedestrians, cyclists, and objects. How do we do that? Okay, pedestrians, we need to be able to provide them notification perhaps. That might be an easy way. So determine that in the patent world, we use broad terms, so we refer to pedestrians as objects often. As we do to cyclists and cars and so on. Determine that the pedestrian's likely to cross the roadway in our way, and give them a certain amount of time to get out of the way. And if they don't get out of the way, we can honk at them. How do I detect a pedestrian? The second one here, characterize a first region of the environment using a laser image and a camera image and a feature vector to generate an object score. So we should call this a pedestrian score, representing the likelihood that they are in a region of the environment that we care about. That is how I will summarize that, and that we need to respond to. Okay, and the last one for the pedestrian, how to identify and respond. Project a grid of cells around the object, the pedestrian, and predict the likelihood that the object will enter a given cell in a period of time. Generate a contour based on those predicted likelihoods. So you can imagine kind of a moving blob of anticipation for that. Now we get into cyclists. This is one that is arguably not all that useful. How to detect a hand signal from a cyclist. And if you do detect one, that will be the first time it's ever been detected in history. Receive a plurality of data points and identify a subset indicative of a cyclist. And based on comparison to cycling signals, determine an expected adjustment of the cyclist's speed and direction. So reading the cyclist's hand signals there. The second one here is how do I detect illumination of the type that you would find on the reflectors of a bicycle. Receive a sequence of time-spaced images where they are illuminated by a light source from the vehicle that is doing the scanning. Detect an object with the size and brightness that can be classified as an actively illuminated or passively illuminated object. And based on that, we can characterize it as a bicycle reflector. And the last row here is how do I identify an inanimate object? In other words, an object that I don't have to slam on the brakes for or run off the road to avoid hitting. How do I identify an object that I can just drive right over and not worry about it? The way we do that, we identify a set of objects and filter to remove the objects that correspond to things we care about, like vehicles, bicycles, and pedestrians, and select the object in the future path of the vehicle and classify it as a drivable or not drivable object based upon its classification. So if it gets checked off, it's not a person, it's not a dog, it's not a cat, it's not a car, I can drive over it. I'm sure the list is longer than that, but that's all that I will come up with at this moment. Okay. That's our pedestrians and cyclists and inanimate objects. Here's your cyclist with a reflector picture. Now we get into weather, and let me pause 1 second here for any questions again. No questions? Okay. Here is our weather. How do we detect fog? A couple of ways it looks like. I receive laser data of the environment. I associate that data with an object and determine from first and second data related to the object and also data not associated with the object that this is representative of fog. So there are some pictures that show that what you would expect to be a complete bumper of a car in front of you is actually partially a bumper and partially a bunch of dots that don't fit with what you'd expect from a bumper, and that's how you define it as fog. The second one is similar in that way. It's associated and unassociated objects of data points, and we determine that that is fog. The next one here is sunlight. How do I detect weather conditions such as sunlight? Receive laser data and associated data with an object. Determine that unassociated data points are representative of an untracked object, and that untracked object maintains a relative position to the vehicle, indicating that the environment is sunny. So there's a bright spot that keeps seeming to follow the vehicle. That is a sunspot. And the last one here is rain or wetness. How to determine if it's a wet surface. Similar as the above, receive radar data from the environments, indicative of tracked objects, identify points not associated with the object, and a surface on which the vehicle travels is wet based upon those unassociated data points. So I'm here in Minneapolis, and it's very glaringly obvious to me that there are not any patents on detecting snow. And I suppose a lot of this is happening in Arizona and California, and that could explain why. But I can tell you there are 52 flavors of snow, and there could be 52 patents for identifying those types of snow. Nonetheless, we will have other problems to solve that are probably more important at the moment. Okay, here are our weather patents. No great pictures to look at there. And then 3.6, we are at emergency vehicles and conditions. There's quite a few on identifying emergency vehicles here. The first group of them is detecting the illumination of the siren, and more specifically, the on and off characteristic or attribute that a siren exhibits. So I receive an image of a second vehicle, and with a first image and a second image, and one of the images shows illumination, the other doesn't. I use that to tell me that it's probably a siren. The second one here, I took this out of the claim language, and I don't even know what this means, but there is a first camera without an ND filter and a second camera with an ND filter and a longer exposure time. I use the second camera to identify the illuminated objects and the first camera to identify the location of the siren. The second group here relates to emergency vehicles. How do I detect an emergency vehicle that shares the road? I access a template of special purpose vehicles, and based on that template, I can determine what kind of emergency vehicle. Is it a police car? Is it an ambulance? Is it a fire truck? How do I detect the presence of an emergency vehicle? I match a trajectory of a first and second vehicle by shape to indirectly determine the presence of an emergency vehicle. So once again here, we're inferring based on traffic patterns whether we have an emergency vehicle in this case. How do I detect and respond to a siren? In this case, I'm going to detect the siren using microphones and estimate a bearing based upon the microphone information. There are some more audio signal methods for detecting the siren here. I am going to receive an audio signal, process the signal into windowed samples with different time lengths, and use that to determine the likelihood of it being a siren. And the last one is not an emergency vehicle, but an emergency condition, a road flare. How to identify a road flare? Detect a bright object on the road, identify it as a road flare if it exceeds a threshold likelihood value. That is the emergency vehicles. There are some black and white images here. And that is the end of chapter 3.